Today we have to start hypothesis test. And everything in statistics is measured by how far away a result is from what we expect it to be. And most things are just, if we want to test a coin, we flip it 100 times. The hypothesis test is a much more formal setup, so that we want to test fertilizer. Does a fertilizer work? So we're going to put fertilizer on something. But we can't just put fertilizer out on the yard and say it grows corn better. You have to control all the things that are in it. And you have to have replication. So we may need 20 farms, 20 fields, 20 acres. But we have to make sure that all those 20 acres are exactly the same. They have exactly the same soil. They have exactly the same rainfall. They have exactly the same bugs, mycorrhiza. Everything about it's got to be the same, except for the fertilizer. So we put on an exact amount of fertilizer, and that's got to be the only thing that affects the corn yield. Anything else that affects the corn yield will just screw up the experiment. So it's really controlled. It's much more strict than what most things are. Like an election poll, they call 100 people on the phone. Well, you have to control all the people. Medical experiments are a real mess to do, because you've got to have people that have the same medical history. If you're going to give them weight loss medicine, you have to have people that are exactly the same in all respects except for the weight loss medicine you give them or don't give them, so you can compare them. And that's so clearly impossible that it's a real mess. So that medical experiments are awful to do. And they're double blind, so that the physician doesn't know what medicine, the patient doesn't know what medicine, so nobody influences anything. Nobody treats them differently. And the ethical concerns are tremendous. If you're giving someone medicine to lower blood pressure, if it does work, well, you just cut off half the people in the experiment, because you can't give them the medicine because you want to know if the medicine works. All of this is part of what's called ANOVA, which is the analysis of variance. So everything is how far are we from what we expect, and we set up the experiment and try to make everything the same except for what we want to test. And that's usually called a factor. So fertilizer is the factor. Statistics started with gambling, and for experiments started in agriculture. So all the good examples are agriculture. And also it's because one of the few things that you can control. But there's a whole world of statistics called experimental design. And this is purely to ensure that the result of any experiment is due only to what factor I'm testing. So that these are very elaborate. And we'll see some of the results when we get to regression, because it's part of the same thing. It's an analysis of variance. The analysis of variance is, does this change things? Does it vary according to what the factor is? That's where it comes from. That's all it is. What we're going to do is the basics of this, and these things are called t-tests. And it's just a stripped down version of what we got. So a t-test is called that because it uses a t-statistic. In this, we have H naught. This is called the null hypothesis. And this is like the status quo hypothesis. If we give these people medicine, it won't change anything. The alternate is called H1 or HA, and fortunately, this is the alternative hypothesis. And the alternative hypothesis is actually what we want to prove. Does the medicine work? So that our null hypothesis for a medical experiment would be the medicine doesn't work. Nothing changes. The alternative hypothesis is something changed. So all of these things are basically this. And the null hypothesis and the alternative hypothesis can't be this works, or this is good, or this is bad. It's got to be a number. So if we're doing blood pressure, it's got to say blood pressure is this, or it's less. We have to have a value for it. The null hypothesis is the probability of heads is 0.5. The alternate hypothesis is the probability is not 0.5. But it's a number. For corn yield, it's got to be, the corn yield is 25 bushels to the acre or less. If I put fertilizer on it, it's more than 25. We expect something, that's the null hypothesis. Does it change? That's the alternative hypothesis. Right? Also, we can't prove anything. All we can do is bet. So even with coins, you're flipping coins, we don't know that the coin is fair. If it comes up heads 1,000 times in a row, we can't say that the coin isn't fair. We can say it's probably not fair. So we're still betting. Now there are two kinds of hypothesis. And all of this is just what you would think would happen reasonably put into fancy terms, statistical terms. A one-tailed test could be the corn yield is less than 25 bushels to the acre. This is H naught, and this doesn't write well. And I don't write well, so everything doesn't look good. The alternative hypothesis is that the average is greater than 25. This is a one-tailed test. I don't care if the corn yield comes up to be 23. If I put fertilizer on it and it comes up to be 23 bushels to the acre, I don't even bother. Because I want the other end. I want the upper end. The other side is just the opposite. The corn yield is greater than 25. Suppose I'm using some kind of nematode control. You familiar with nematodes? You learn all kinds of obscure things when you deal with statistics. Because I know the statistics, I don't know the science of the thing. Nematodes are little worms in the soil, like this long. And if you get nematodes, they'll eat the roots. Right, so I've got a one-tailed and a two-tailed hypothesis. And I have to know where to cut it off, where to say the fertilizer worked, or the nematodes control made the corn yield go up. Also, all of these things that you see in the book or online, they may say, for the null hypothesis, the mean is equal to 25, and the alternative is that it's greater than. Right? To me, this is not what I learned. It's this or that. You have to cover all the possibilities with the null hypothesis and the alternative hypothesis. So you'll see this, that means this. This is what I'll write, this is what they write. The important thing is always the null hypothesis, because that's where we get to make our judgment. Right, these are called one-tailed test, because if I'm looking at the 25 equal to or less than or greater than, it's the null hypothesis that just sits there. It's the alternative that controls the show. So if I'm looking at a distribution, and this is all odds again, here's my distribution, and there's the null hypothesis mean. If it's a one-tailed test, and this is called a right-tailed test, because that's where I'm looking to see if I can find an effect. I have to have a cutoff in the right tail of the distribution to say, yes, there's an effect, or no, there's not an effect. If it's the other tail, left-tailed test, the cutoff is on the left side. And this is all reasonable. If I do fertilizer on the corn and I get 25 as a result, yeah, okay, that's what I thought it was going to be. It would have to be more than 25 to say there's a result, and it's got to be a big enough effect that I can say, yes, this probably is true. And again, I can't say it's true, I can only bet that it's true. On the other end, with the left-tailed hypothesis, the result would have to be less than 25 before I can say, yes, this is probably true. So the difference is, which way does the alternative hypothesis point? This cutoff here or here, and this is just flipped. There's no intrinsic difference between these two things, except I'm looking at this end or I'm looking at this end. All the odds, all the probabilities are all the same. This is called the rejection region. If my answer falls into that tail, I reject the null hypothesis. If it doesn't fall into that tail, I can only fail to reject the null hypothesis. I can't say the null hypothesis is true or the alternative is true. I can reject the null hypothesis or fail to reject. And it's pure statistical wording because I can't prove anything with statistics. I can't say for sure. This is like Schrodinger's cat, which is a good example because there's no example. The cat, according to Schrodinger, is alive or it's dead, and I don't know it. I never know that I got it right. All I can do is say, if it's in the rejection region, the null hypothesis is probably not true, and I reject it in favor of the alternative. So, rejection region on one side, or the rejection on the other, the alternate hypothesis always points to the critical region, the rejection region. So that if it's less than 25 or equal to for the null, it's greater than 25, and that alternative points to the right. The other way, it points to the left. So you always know where to look. And this is just reasonable. If I do a corn yield experiment and I don't get up to 25, I'm not even interested. I'm not even going to test it. This doesn't work. There's no chance that it works because I'm not there. So it's got to be to the right. This is also called a critical region. So rejection region and a critical region are the same thing. Right, rejection region is the reasonable name for it. Critical region is the statistics name for it. Because I have to have a cutoff value. So flipping coins, at what point do you say, this is probably not true? We flip a coin 3 times, it comes up heads 3 times. No big deal. You do it 5 times and it comes up heads 5 times. You might be beginning to suspect that. But where's the cutoff? Is it 6? 7? I know if I do it 100 times and it comes up heads, that's not going to work. I don't believe the coin is fair. If I do it 3 times and it comes up heads, I believe the coin could still be fair. Somewhere in that range, I've got to have a cutoff. And I have to decide, is it 6, 7, 8, 9, 10? This is called the critical value. And it is literally how many heads before I say the coin is probably not fair. And I have to choose that. And statistically, I can design the experiment. I can analyze the experiment. I usually don't get to conduct them because they got equipment for that. We did experiments with turtles. A graduate student had to go live on a beach in Florida for 2 summers. This was terrible. And twice a day, he would walk down the beach and mark turtle nest. You've been to the beach, you see the marked turtle nest? His job was to find the turtles as they came in, and he measured the turtles. He had to not interfere with them, so they had to lay the eggs first, and they come in at night. So he's hanging around the beach at night in Florida. This is a terrible job. What did I get? I got a bunch of data. So if you've got a chance between analyzing the data and measuring the turtles, go measure the turtles. But here, this is called the critical value, and it is set as an alpha level. And this is exactly what we did for confidence intervals. Confidence intervals was, where's the cutoff? What's the probability that I'm outside this region? So the alpha level is the percent of the distribution in the tail. And it's usually 0.05. 5% in the tail is the cutoff. And I need a t value or a z value that cuts off 5% in the tail. So here, my cutoff, whatever this distribution is where is the 5% line. And most experiments are run on alpha equals 0.05, not because that's something good. It's because that's what's accepted. I have never seen an experiment done with anything other than a 5% or a 10% alpha level. Simply because 5% is what is traditional and 10% is convenient. People understand 10%. If you're driving down the road and a car comes by you, you know how fast that car is going. You don't know exactly, but you know, is it going 10% faster? If it's going twice as fast, you recognize that. Is it going 1% faster? Then you don't know. So these are simply matters of convenience, or what people expect, or what they will accept. So 5% is just kind of traditional. That's a one-tailed test, left tail and right tail, with an alpha level that cuts off the critical region. And I have to find the value of the t or the z that cuts that off. The other kind of test is called two-tailed. And this would be more like flipping coins. I have a null hypothesis, H naught, which is why it's called null. The 0 was a null, H naught, and this dates back so long ago that, well, you can find the first instance because it's not that old, but that's just the name of it. This would be the probability of a heads is 0.5. The alternative is that it's not 0.5. So I've got one-tailed test, right-tailed or left-tailed, tells me where the critical region is, the rejection region. And the alpha level tells me how big it is. The two-tailed test is both ends. It doesn't point to one end or the other. It points to both of them. And if the alpha level is 0.05, I have 2.5 in each end. So that's the setup. Two-tailed test just puts the critical region on both ends and splits it in two. And it's always symmetric. If it's 0.05, overall it's 2.5 in each end. Okay, where's that? Blood pressure. Write down, so you have done it once. What's normal blood pressure? What do you know about blood pressure? Systolic. I want to give blood pressure medicine. The test is, does it help? Write down the null and the alternative hypothesis. We got paper here, just so you've written it down once. That's the only goal of this, is to write it down once. So get something, write it down. We got paper up here. What's the null and the alternative hypothesis? And there's no reason to do this other than do it. Normal blood pressure is 120, supposedly. The null hypothesis is it's not going to change if I give someone blood pressure medicine. What's the alternative hypothesis? Yeah, write it down. It's H1 or HA, and whether it's H1 or HA actually depends on where you went to school, where you got your degrees. If you're on the West Coast, from Iowa over, it's H1. If from the East Coast, it's HA. And I have no damn idea why. There's a familiar with race horses? Enough to know that if you've got a racehorse that wins a lot of races, then people want their offspring. Right? In statistics, there's a similar setup, and math is, who is your major professor? Where did you go to school? So that if you're from Iowa State, that's where the experimental design people began, because it was agricultural experiments. So Iowa State has these guys, and the names are here, and then their offspring, so to speak, are the students that they had, who later had other students, and so on. So, statisticians and mathematicians are like racehorses. You ever hear of an Erdos number? There was a mathematician named Erdos. He was Hungarian, I think, originally. And he was really, really very strange. And you can look him up. He would go to a place. He never had a regular job. People would hire him to teach things or whatever. But he would show up and he would start talking about a math problem that he was thinking of. So he'd go to some other mathematician's school, and he'd just walk into the office and he'd start talking. And they would do proofs, mathematical proofs. And an Erdos number is the number of people that were on publications with him. So if you had an Erdos number of 1, that meant you had been on a publication with Erdos. If your Erdos number is 2, that means that you were on a publication with someone who was on a publication with Erdos. If you had an Erdos number of 3, it was you were on a paper with somebody who was on a paper with somebody who was on a paper with Erdos. And incidentally, Pablo Chalmeta, the head of the Department of Mathematics, has an Erdos number of 3, right? Which, in the math world, all right, and you've got to remember who you're dealing with here. He's an important person. Does it help him cash a check? Yeah. But, so, my problem is, I'm from the East Coast. I have a degree from Virginia Tech. Then I went to Oregon. Right, so all of my East Coast stuff suddenly is West Coast stuff. Then I went to Georgia. So now I'm back on the East Coast again. Right, so what you see here, the HA and the H1, is where the hell have you been? And who were you talking to? So all of it's like, all of this stuff, all the math, all the statistics, it isn't like literature. In literature, Emily Browning, is that her name? Bronte. Who wrote the poems? All the poems that can be sung to the Yellow Rose of Texas. You might look that up too. They don't have a list of connections. All right, mathematicians and statisticians have ridiculous connections. So that's why you see some things and some things you don't see. And if you went somewhere else, you would see something expressed differently. And I only tell you this because this always fascinated me. Why the hell is that? So one's one coast, one's the other coast, and there's absolutely no difference. Purely, where did you go to school? All right, so what's the alternative? Write it down. We're just writing numbers and names. What's the alternative? Which way does it go? Goes the other way. Where's the rejection region? The critical region. Draw a picture. Here's my 120 in the middle. This is what I expect. Where's the rejection region? Which way does the alternative point? And literally, if you treat it like an arrow, which way does it point? Right? Now I have to find a value for the cutoff. You'll need XL. And we need a T distribution. So you need to start XL, and we need a sample size. And say we've got 50 people. For an alpha of 0.05, what is the value of the cutoff? What value of T? And I've got two scales here. This is the actual. We'll call this X. This is the T. Yep, got away. Zero's in the middle, and it corresponds to the 120. To find the cutoff value of T, I have to use the T.inv. In XL. We just need XL. I need equals T.inv. And it tells you what you need, so that for a 5% cutoff on the left tail, I need 5% to the left. In these functions, everything comes from the left, so the probability I want to put in, and if I put in the paren, it tells me what the rest of it wants. Probability is going to be 0.05 because I want 0.05. The next thing is the degrees of freedom. I have a sample size of, what did I say, 50? What's the degrees of freedom? No thought. What's the degrees of freedom? 49. Just subtract 1. And incidentally, degrees of freedom is much more complicated than that. But for what we need, it will never be anything other than n minus 1. 49. So my cutoff t value is minus 1.67, 1.68, however you want to look at it. So here, I need this, minus 1.68. I'm going to do an experiment, and my result will be a sample mean. The mean blood pressure of these 50 people. And I need it to know, is that result more than 1.68 standard errors below the average? So I got two scales running. One is 0, and the other is the actual. This here corresponds to no difference from the average. And this is if you use the z value instead of the t value. It's going to be, I'll put it in there. What's the normal distribution, standard normal distribution, analog to the t.inv? Again, no imagination in Excel, equals, it's a normal, what's it start with? NORM. And I get a list, norm.s.inv, and all it wants is a probability, and I'm using alpha equals 0.05. That's the difference between using the t distribution, which is concerned with small sample sizes, literally samples of size 5 or 4, because that's what the guy who was making beer was dealing with, and the z value, which is minus 1.645. So basically there's no difference between these two things, but this is why it's called a t-test rather than a z-test, because I've got t for the cutoff. All right, I do this test. There's my blood pressure example. And all of these are entirely fabricated. There's not a truth in here. Nothing is real. I do a test and I get, out of 50 people, I get an average of 100 and the null is 120, this is 114. I give the people blood pressure medicine, and I get their average blood pressure, and it's 114. The standard deviation of that is 21. Everything is measured in standard deviations or standard errors. I need the standard error for this. What's the standard error? How's it calculated? What do? It's always the same thing. And these are the only two calculations you ever need to know. One of them is standard error, and the other is add or subtract standard errors. 21 divided by the square root of 50. So put that in there. What do we get? How much? 2.97. Okay? Now, I never know quite how to approach this because I can do it from two directions. We can go from the t to the x, from the 0 minus 1.68, or from 120 to the equivalent of that. So if the standard error is 2.97, what is the value that cuts off 5% from the x distribution? Here, this says I have to be more than 1.68 standard errors below the average. How many, or in blood pressure, in millimeters of mercury, I have to be minus 1.68 standard errors below the average, 1.68 times 2.97. I need 1.8 times 2.97, 1.68, excuse me, times 2.97. And what is that? 2.97, 1.68. This is minus 4.989. That means my cutoff value on the X scale is minus 4.98 from 120. So this is basically 5. My cutoff is 115. Or 120 minus 4.99 is the average from the experiment further from 120 than 115. Basically, is that result in the rejection region? And 114 is outside of the normal part. It's in the rejection region. I would reject the null hypothesis that there is no effect of medicine. Basically, the medicine worked. The other way to look at this one I went from how far I needed to be and how many standard errors it was to how many is it really. My result was 114. And this calculation is always x bar minus the mean divided by the standard error. Basically, how many standard errors from the presumed average is the result. So I have 114 minus 120 divided by 2.97. What do I get? This is minus 6 and 2.97. How many standard errors is my result from 120? And it's minus 6, 2.97, is equal to 2.02, negative. Here's my t-scale. My cutoff is minus 1.68. That's the 5% cutoff. Is my result further out than that? Is the minus 2 in the rejection region cut off by minus 1.68? And Here's minus 2. Okay, so this one, this direction, and it literally is which way am I looking at this thing. If I look at it from the experimental result side, I get a 114. The presumed average is 120, and the standard error is 2.97. Is 114 far enough from 120, measured in standard errors, to go into that rejection region? And it is. So I would reject the null hypothesis that the medicine doesn't work. I am rejecting the null in favor of, yes, the medicine worked. What's my chance of error in this experiment? That's the alpha level. That's how I choose the alpha level. It's what the chance is that I got it wrong. What's the chance that just out of the blue, this experiment gave me a result of 114? That's what the 0.05 is. Okay? Everything from here on is, what do you believe and what's the probability? Right? And all we're going to do is do different versions of this for the next week, presuming we don't get tornadoes or snow, which around here seems to be reasonable. Or we can't rule it out anyway, which also is statistics. Okay? All right, all done. Go away.